Okay, it's 3:01, so we can start with the colloquium. So welcome to the second Cairo colloquium this semester. And today we have Youngsoo Choi from Lawrence Livermore National Laboratory. And he will talk about physics-constrained data-driven physical simulations using machine learning. And before he's starting his interesting talk, I would like to read his bio. So you have a little bit more details about our today's speaker. And so, yeah, let me start. So Youngsoo is a computational math scientist in CACS and a computing doctorate at Allen et al. He is currently leading data-driven reduced order modeling development team for various physical simulations, with whom he developed the open source code librom and Lagos ROM. librom is a library for reduced order models, and Lagos ROM implements reduced order models for Lagrangian hydrodynamics. He has earned his undergraduate degree for civil and environmental engineering from Cornell University with applied mathematics as minor, and his PhD degree for computational mathematical engineering from Stanford University. He was a postdoc in the National Laboratories and Stanford University prior to joining LLN in 2017. So welcome, Youngsoo, and we're looking forward to your interesting talk. So the stage is yours.
All right, thank you so much for the invitation and wonderful introduction, Patrick. I'm very grateful for this opportunity, by the way. I hope this opportunity will lead to another opportunity of collaboration between LSU and the Lawrence Livermore National Lab. Today, I would like to introduce many exciting data-driven physical simulation capabilities we have developed in the past several years here at Lawrence Livermore National Lab. This is exciting field of research right now, so I'm sure that you will enjoy the talk today. All right. I would like to recognize my collaborators and team members. Of course, all the results I'm going to present today were not possible without these awesome people. All right, let's start by arguing about the physical simulations. There is no doubt that physical simulations are so essential for the advance in science and technology these days. Well, then how did we get the physics simulation capability, which we are heavily relying on today? I would argue that data already played an important role in the past. Just to illustrate, if you look at how we have advanced the orbital model of the solar system in history, it starts with Copernican model, which correctly postulated that planets orbit sun, not the other way around, right? But he used the telescopic observations of the phases of the Venus to conclude that that results, right? Then Kepler interpreted the more observational data of planetary motions by Tycho Brahe to develop Kepler's 3 laws of orbital motions. Then Newton further developed laws of mechanics, gravity, and calculus, which is further advanced to differential equations. Then many physics laws were written in terms of differential equations later on, such as Navier-Stokes equations, Schrödinger's equations, wave equations, and many other equations of motions. Then computer came along, greatly improving computing powers as well as the numerical methods of solving these differential equations, thanks to Hilbert, Courant, and many other pioneers. This is how we have now physical simulation capability that is advancing science and technology these days. For example, you are looking at a beautiful simulation modeled by smooth particle hydrodynamics for shaped charge penetration. This simulation is well matched with experimental data. This kind of simulation can be run routinely for various applications. However, it has limitation though, that is, it can be very computationally expensive. For example, one Ford simulation of this shaped charge simulation takes 7.4 days. This is unfortunate in multi-query applications such as design optimization and uncertainty quantification, where you have to run these fold simulations many times while you are exploring your parameter space, right? Therefore, we need reduced order models that accurately accelerate these expensive physical simulations. Here again, data will play a key role of building an efficient reduced order models. A reduced order model can be built by using data. First, considering a parameter space, D, which I denoted as D here. Then the parameter space can be anything you would like to explore. Like it could be initial condition, boundary conditions, or material properties of your the simulations, etc. Then you collect simulation data by solving full order model with high performance computing, for example, for several sample points in your parameter space, right? Then you apply machine learning techniques to build a reduced order model to the data you have collected. And various machine learning techniques are available as listed here. So various reduced order modeling types are possible, but depending on how much you incorporate physics law in the reduced order model, it can be intrusive or non-intrusive. I will go over some advantages and disadvantages of intrusive and non-intrusive methods in the next slide. But once the reduced order model is built, you can accelerate simulations and predict the solution at various query points here and there, and many other points which you have not seen in your training phase. So it is definitely the predictive, right? All right, these reduced order models can be categorized by its level of intrusiveness. For example, the black box approach denoted as BB here is using only data. So it is least intrusive method, right? Then we can think of more intrusive method, which is the linear subspace reduced order model, so-called LSROM, where you incorporate the physics and your state fields are represented by a compact linear subspace. And even more intrusive methods, that is nonlinear manifold reduced order model, so-called NMROM, where the state fields are represented by a compact nonlinear manifold. Roughly speaking, more intrusiveness means more accuracy, so the intrusive reduced order models are more accurate than the black box approach if the same amount of data are used. On the other hand, more intrusiveness means less speed up. So the black box methods is faster than the intrusive reduced order models in general. Also, the physics constrained reduced order models are more robust in extrapolation than the black box reduced order model, which will become handy in multi-query applications such as PDE constraint optimization. All right, let me try to introduce three different non-intrusive reduced order models. The first non-intrusive approach is the linear multi-step neural network. This method uses the linear subspace dimension reduction approach, so-called the proper orthogonal decomposition, and proper orthogonal decomposition can be accomplished by the singular value decomposition, so-called SVD. And to demonstrate that, let's say we have a airfoil simulation data denoted as the W here. We use singular value decomposition to obtain a reduced basis for the solution variable. We denote the reduced basis as a phi, and then project the data W onto the subspace spanned by phi by multiplying phi transpose from the left to the W, and we form reduced spaced data denoted as A. Then the linear multi-step neural network is trained using the reduced data A, and also associated parameter you are trying to play and tweak or explore in your the parameter study, in order to propagate in time in the reduced latent space. Then the full state is restored by the reduced basis phi. As you can see, we have only used the data, nothing else. We didn't use any physics information. So this is basically black box reduced order models. By the way, this type of reduced order model is called latent-based learning approach. The latent-based learning approach has two main steps. The first one is the compression step, and the second one is identification step. For example, this linear multi-step neural network used the linear compression, which was using the POD and SVD for the compression step, and the linear multi-step neural network for identification step. All right, let's see how it performs. We have applied this linear multi-step neural network-based black box approach for a steady flow around the airfoil simulations. Here, we change the Mach number to generate simulation data and compress them using singular value decomposition and train the linear multi-step neural network, as I explained in previous slide. As you can see that the predicted solution by this surrogate model and full order model are identical in eyeball norm, while the surrogate model takes only 2.55 seconds, while the full order model takes 314 seconds, giving us a speed up of greater than 100. Quantitatively, the relative error we achieve is less than 1% everywhere. Basically, in eyeball norm, you cannot distinguish those two solutions. So, which is pretty good. All right. Another way of the compressing the original physical data is using nonlinear compression techniques. And one representative nonlinear compression technique you can use is autoencoder. Autoencoder consists of the two parts. The first one is encoder, which reduces the original data W to latent space, and then decoder, which maps back to the full state again by decompressing the reduced data to the full state. And you train this autoencoder by comparing the difference between this approximated flow W tilde and the original W, and minimize that to train the neural network in the encoder and decoder. And once you train that encoder and decoder in the latent space, the data becomes the all latent space the data, and you can apply the interpolation techniques such as the radial basis functions or the artificial neural network and any other like the interpolation, your favorite interpolation techniques, and train them and use that to predict the latent space solutions for new parameter value mu star. And once you get the latent space solutions, you can apply the decoder to reconstruct the full state predicted solutions. That's how the procedure goes. And since we were interested in, okay, now we have applied the nonlinear compression techniques. Previous examples, we used the linear compression techniques. And what is the benefit of using the nonlinear compression technique, right? So in order to see that, we have compared those two techniques on the porous media flow simulation. And we found that the problems with the porous media simulations, when the advection dominated the solution characteristics are dominant, then actually the nonlinear the compression technique outperforms the linear subspace technique, which is the POD or singular value decomposition. So that was nice discovery to find. And the last the black box approach I would like to introduce is the deep fluid, where again the autoencoder is used for compression and decompression of the solution data W. And only difference from the previous example is that the latent space dynamics are being learned by the latent space integrator after the autoencoder is trained. But the rest of the procedure is the same. You use this latent space integrator to predict the solutions in the latent space and apply the decoder to reconstruct the full states again. All the same or same old, right? And we have applied this deep fluid black box approach to 2D burgers, the problems where the simulation is very advection dominated. As you can see from the movie, a shock front is formed from the left bottom corners, and then it propagates to the rest of the computational domain. And the deep fluid gives, it's doing pretty well. I mean, as you can see from, as you compare these two movies in eyeball gnome, the deep fluid solutions are pretty much, capture the dynamics of the full order model very well, using only the latent space of the 5. However, quantitatively, though, the deep fluid gives the maximum relative error of 38.6%. This might be good enough for the animations or the digital graphics, but it is a bit too large for scientific applications, right? So for a better accuracy, the conclusion is that we need to incorporate the existing first principle, or you have to incorporate the physics information into your reduced order model. All right, one way of accomplishing, incorporating the physics information into your reduced model is by the traditional projection-based reduced model. To explain that, we will start with this governing equation represented by the ordinary differential equations here. You can think this ordinary differential equation as the semi-discretized version of the partial differential equations, which describes your physics, right? Here, W is your the state variable, F is your nonlinear terms, and T is your time variable, and mu is your parameter. And we first approximate the solution, the W, as a linear combination of reduced basis phi, whose dimension is a lot smaller than the full order model dimension, big N sub S. Here, the keyword is the linear subspace. Then you plug the solution representation into the governing equations, right? You plug this going back to the governing equation wherever W occurs. You replace that W with this linear subspace, representations. And by doing so, your unknown is W hat, which is a lot smaller size than the big W. So you just decrease the total number of unknowns from big N sub S to small N sub S. Big N sub S here can be like million or billions, and small N sub S can be 10 or 20, very small number. So your original the equations now becomes overdetermined system, meaning that you have more equations than unknowns. So in order to close that overdetermined systems, one way of the closing those overdetermined system is by Galerkin projection, which is done by multiplying the basis matrix phi transpose on the left and right hand side, and that will gives you the closed reduced system of equations you have to solve every time step after you apply your favorite time integrator, right? But here is the catch. If you are dealing with a nonlinear term, for example, if this F is varying nonlinearly as the W changes, then every time this argument W hat changes, you have to update the nonlinear terms, and you have to multiply again this phi transpose by this updated the nonlinear terms, unfortunately, which scales with the full order model size. So without any special treatments, it is well known that this projection-based reduced model for nonlinear dynamical systems like this is actually slower than the corresponding full order model. So what's the point of introducing this linear subspace reduced order basis representations and going through all these hassles? And at the end of the day, it's slower than the full order model, and the accuracy is still approximation, right? So no point. So in order to get the speed up, you need to apply so-called hyper reduction, which brings the complexity of the full order model size due to the nonlinear terms, bring down the complexity into the very small complexity. Okay, the most famous hyperreduction technique is DEIM, which stands for discrete empirical interpolation method. The DEIM introduces the nonlinear basis phi of F, and then express the nonlinear term as a linear combination of nonlinear basis vectors. Then it introduces a sampling matrix Z, which is the most crucial things in this hyperreduction. The sampling matrix Z selects on just the subset of the nonlinear term outputs. So after the action of Z on the nonlinear term F, you only need to evaluate only the subset of F, not the full, order size of the F. So that's where the efficiency coming from. Okay, so once you train the Z matrix, once you come up with the Z matrix, even before that, how do you get the sampling the matrix Z? There are various the algorithms available. I will not go into detail, but DEIM and QDEIM are the popular ones. But let's say you have obtained the sampling matrix Z, then the generalized coordinates for nonlinear term f of hat can be obtained by solving the interpolation problem. And this is the solution of the interpolation problem, and you plug that back into the reduced system of equations wherever the nonlinear term shows up. Then you will end up with these crazy looking equations, but don't be panic, because a lot of terms here can be pre-computed. Once it is pre-computed, you can just stick with those the matrices, and then more nicely this Z transpose F, because of this sampling matrix Z transpose in front of the nonlinear term F, you do not need to evaluate the whole, the F vectors. You only need to evaluate only the subset of that. So, which is ultimately the way of, achieving a efficiency through this projection-based reduced model. All right, there are many other the hyperreduction techniques, the variants of the DIM, so like GNAD, ST-GNAD, and the SNS method. However, they are more or less similar to what I have just described in this slide, the DIM. All right, this traditional linear subspace reduced model can be used to accurately accelerate the various physical simulations, achieving a speedup of 10 to 1000, or sometimes even higher than that, with a relative error less than 1% or 5%, or accurately speaking, with a tunable accuracy. You can control your accuracy. If you want the accuracy to be like less than 3% relative error, then you can achieve that, fine-tune that by maximizing the speed up and by tuning the reduced model techniques, reduced model the parameters. So that is the very nice thing about this type of projection-based reduced model. All right, let's look at for example, how this linear subspace reduced model has been applied to various simulations. Here I'm showing the applications of Lagrangian hydrodynamics, which is not particularly easy to apply the traditional projection-based reduced model, because as you can see, it's advection dominated, right? And it's causing some challenges to the traditional linear subspace reduced model to accurately capture the solutions of this advection dominated problem. But our team has developed time windowing approach, and we were successfully was able to obtain a speed up of 14.6 and speed up of 22.8 and 31.2 and 87.8. with an accuracy which is less than 1% relative error, of sometimes even less than 0.1% error. Basically, it is, if you compare the solution of the float model with a reduced model, you cannot compare the distinction with eyeball numb. So this was really, we were very excited to see this kind of results. And another great thing about the projection-based reduced model, the physics constraint reduced model, is that its speed up will increase as we apply it to larger scale problem. Just to see that effect, we have refined these Rayleigh-Taylor instability problems and observed the speed up. As you can see from the graph, a higher speed up is achieved as the size of the problem increases. Another great thing about this reduced model is its robustness with extrapolations. Unlike the black box approach, since the reduced model directly incorporates the physics, the information, governed, described by governing equations for the underlying physics, even though it is used to predict the solution for the parameter point away from the training data. For example, we have build a reduced model at the blast energy of 0.25 here, and then look at the accuracy around that 0.25. As you can see, the accuracy, it deteriorates because it will be most accurate where the ROM is trained. But outside of that, extrapolation regions, the accuracy will deteriorate. However, not much. As you can see for these problems, still 1% relative error is achieved by around like from 0.1 to 0.4. So that area, that region becomes a trust region of these local reduced models. And you can imagine that in order to build a reduced model which covers the whole your parameter space, you can simply create another reduced model here and bring the trust region over there, and the trust region of this local reduced model and trust region of this local reduced model will cover the whole parameter space, so that the total, the overall, the accuracy will be desirable accuracy, right? So that's another nice things about this projection-based reduced model. And another the nice thing, or is the implication of this, the robustness of this extrapolation, is that it can be used to efficiently approximate the gradient information, for example, which will be very useful for design optimization or in general in PD constraint optimization. So if you have done some research on this area, computing the analytical the derivative of the PDE is pretty challenging. So but if you have these local reduced models available, which is good in the extrapolations, then you can think of approximating the derivative with a finite difference, where this perturbed function evaluation can be efficiently predicted by this local reduced model using the robustness capability of the physics constraint ROM, right? So that is a great tools. Okay, going back to the comments I made about the trust regions, right? I mean, yes, you can pick a bunch of the local reduced model and make sure the overall the accuracy will be below the desirable the target accuracy, like the less than 1% relative error or 3% relative error. But we don't want to build a local reduced model, just blindly, in anywhere in your parameter space. We would like to minimize the number of reduced model we would like to build as small as possible, because in order to build a local reduced model, you need to collect the full order model simulation data at that point, and the generating those simulation data at that point is very computationally expensive. So in order to optimally sample the points in your parameter space, we are going to apply a greedy algorithm. And okay, this movie, oh, it worked before, right? Okay, great. And in greedy algorithm, it chooses the sampling point using the physics-informed error indicator. So for example, let's going back to the seed of blast problem, and let's say we would like to capture the solutions between the blast energy of 0.075 and the 1.25, and any between the number between those two, we would like to precisely predict the solutions with the accuracy level less than 3%. How are we going to do that? In greedy algorithm, you are going to start with a initial local reduced model. the natural choice of the initial position would be the middle point, right? Let's say. And with this local reduced model, as we have seen before, the extrapolation regions, as you go away from that point, the trained point, the accuracy will deteriorate, right? Which is depicted by the blue dots. And we do not compute the actual relative error here. Instead, we use the error indicator. The popular error indicator is the residual-based norm error indicator. And by doing so, it avoids of calling or solving the full order model, the states, and get the relative error on those points. This error indicator is going to efficiently tells you, okay, how bad your accuracy would be for this local reduced model. Okay, so from there, we can find out where the maximum relative error occurs in the greedy algorithm. This point is the maximum relative error, maximum error occurs, right, based on the error indicator. And we build another local reduced model at that point that will bring down the error, it will improve the accuracy around there. And then find out the next, the maximum error, which is here. And then you add the local reduced model and you repeat this process until this desirable accuracy, 3% relative error, the measure is met. All right, here is a actual results of the greedy algorithm. Our target relative error was 3%. And this greedy algorithm spits out, this 15 the sample points, and this 15 sample points, we were able to get the relative error less than 3% everywhere in your parameter space. And as you can see, this sampling, using the physics constraint, physics informed the error indicator, it samples more for the lower the blast energy regions than the higher blast energy regions. You wouldn't be able to guess using predefined the sampling algorithms, such as the Latin hypercube or the uniform sampling. You wouldn't be able to achieve this kind of optimal samplings. It was possible because through the greedy algorithm and because we were using the physics informed error indicator. All right, this results which we were pretty excited about. The detailed description of that is written in this paper. And I would like to now take a chance of introducing our software called the Libram. And this linear subspace reduced Dodo models I have described in this talk. You can actually download this open source Libram library, and you can actually get your hand study by generating the results I have shown in previous slides yourself. And the Lagerstrom and Libram will let you do that. It's open source. So you can go there and download it and try to start to playing around. And on top of that, recently we have launched a web page for the Libram, and some important, interesting the informations are there. And also we have made the YouTube tutorial, describing what the projection-based reducer model is, and we are going to continue to make this YouTube video. Each YouTube video is only like 10 minutes or 15 minutes long, so it's not that topic by topic. So you can choose those YouTube video and then take advantage of it. All right, so just to give you a snippet of the Libram, some major features we have in the Libram includes the proper orthogonal decomposition, such as the static singular value decomposition, incremental SVD, randomized SVD, or space-time SVD. And the famous the data-driven physical simulation technique called the dynamic mode decomposition. By the way, this is not physics constraint. It is it is a black box approach, but it is widely used, popularized by the Nathan Kutz and the Stephen Brunton University of Washington, and originally developed by pioneered by the Ego Magic and etc. And we have also the examples of how the dynamic mode decomposition performs, for example, on advection problems and the Euler equations, and also the heat conduction the problem, and nonlinear elasticity problem as well. And of course, we do have examples for the projection-based reduced model, which is physics constrained, and you will find the example of Poisson equations and the nonlinear diffusion problem and Lagrangian hydrodynamics problem. And you can actually generate those results using the libram. And of course, the greedy algorithm I have described in previous slides is also there, and you can take a look at that. All right, let's go back to the 2D burgers, the problem, by the way, just to actually introduce some drawbacks of the linear subspace reduced model. So, okay, this example, 2D burgers, advection dominated problems, you have seen, the applied, the deep fluid, the method, the black box method was applied before. Now let's apply the linear subspace reduced model to these 2D burgers, the problems. And as you can see, latent using only the latent space dimension of 5, it does pretty good job, but the LS-ROM, there is some fictitious oscillations shows up in the front of the shock wave, right? So this brings down, worsen the relative error. It gives you the 34.4% relative error, and speed up, although it gives you the pretty good speed up. So it's not hard to see why the linear subspace reduced model struggles with these advection dominated problems, because since we are using the simulation data to construct the reduced spaces, the linear subspace reduced model cannot compactly, represent the linearly independent, the advection dominated snapshots, right? It's impossible. So that's why we apply the time windowing approach, where we, decompose the time domain into smaller subdomain, and we only construct the linear subspace reduced model for each subdomain, right? So that's one way of doing that. But what if we would like to address this issue with another approach? And that's where the nonlinear manifold reduced model, the method comes in. The nonlinear manifold reduced models, to explain that, let's go back to the governing equations described by these ordinary differential equations. And here W is your state variable, right? And again, we do the solution, you accomplish the solution approximations. And instead of the linear subspace solution representation, we are going to introduce the nonlinear manifold solution representation through this nonlinear map G, which maps the small latent space to the full state solutions. And by doing so, we are decreasing the number of unknowns from a million billions to 10 or 20 efficiently. But because of this nonlinear fashion, it is nonlinear manifold reduced model basis representation. Well, then you can ask me, how are you going to obtain this nonlinear map function? We are going to actually use the nonlinear compression technique, which you have seen in this talk, which is autoencoder. Remember, in autoencoder, there is 2 parts. Encoder compresses the full data to the small latent space, and then the decoder decompresses the small latent space back to the full state. If you look at this decoder carefully, it is basically a nonlinear map which maps the small latent space to the full state. So this is a perfect candidate for this nonlinear map for this solution approximation representation. So we plug we use this decoder as a nonlinear map. And once you train this autoencoder, we can get this solution representation, and we can plug again back to the governing equations wherever the W occurs. Remember, the governing equation is a representation of your underlying physics. So since by the fact that we're plugging this social representation into the governing equations, it is our reduced order model respects the underlying physics, right? Which is described by this governing equation. But once you do that, as in the linear subspace reduced model, the system of equations become the overdetermined system again. More equations than unknown, because the number of unknowns has been reduced through this nonlinear compression, the G functions. So you definitely need to close the system, and you can close the system by applying either Galerkin projection or the Petrov-Galerkin projections. But notice that this nonlinear function G is the nonlinearity we did not have in the original governing equations, right? So in some sense, we are adding more nonlinearity to the original nonlinear functions. So the problem itself becomes more complex because we are making more nonlinearity. So definitely in this nonlinear manifold reduced model, it is crucial to apply this hyper-reduction technique I have described in previous slides, very efficiently in order to achieve the efficiency. But when you apply the hyper-reductions in the nonlinear manifold reduced model, it is very the structure or the design of the neural network dependent. In order to explain that, let's say the hyperreduction chose these three outputs of the nonlinear terms needs to be evaluated. And in order to evaluate that through the decoder, for example, if the neural network, the design is deep, then you have more than one hidden layers. And as the number of hidden layers increases, the hidden nodes connected to these selected outputs, the number of them is increasing as you go from one layer to another layer and to the another layer. And basically, as the number of hidden nodes are connected to the outputs are increasing, for example, the computation of the Jacobian of this neural network is more computationally demanding. Otherwise, on the other hand, if you choose to use the sparse and shallow neural network for your decoder, then the number of hidden nodes connected to the outputs are very small. And if we sparsify the neural net structure, then the number of hidden nodes connected to the outputs is even smaller. Therefore, the computation of the Jacobian, which is required for the solution process of the nonlinear manifold reduced model, can be done very efficiently. So that's how we achieve the ultimate efficiency of the nonlinear manifold reduced model. And when it is applied to the 2D Burger's advection dominated problem you have seen before, it basically gives you the accuracy which is not distinguishable from the full order model solution in eyeball norm. But not only the eyeball norm, quantitatively also the relative error of less than 1% is achieved. And thanks to the hyperreductions and thanks to the sparse, the shallow neural network structure we have, the speed up was 11.6, which was not possible in the past. All right, so right now I have, the time is 1:45. I guess I can briefly mention the next two topics, and then we can move on to the Q&A session, I guess. Okay, the next topic I would like to introduce is the space-time reduced model. If you think about it, the way I have reduced the number of variables, if it is the time-dependent problems, then I have only reduced the number of unknowns in spatial degrees of freedom. But for the time-dependent problem, there is a temporal degrees of freedom also. So nothing stops you that to reduce those dimension, temporal dimension also. So what does the space-time reducible model achieves is it introduces the reduced basis for both spatial domain and temporal domain in order to maximize the reductions. So, by constructing this space-time basis, you can follow the similar procedure I have been describing so far, like plug that basis into the governing equations, and then you do the hyperreduction to reduce the complexity of the nonlinear the behavior, and then et cetera, you will get the great speed up and accuracy. As an example, we have applied this space-time reduced order model to large-scale particle transport problem, where the spatial degrees, it has a spatial degrees of freedom of around 700 million. And if you count the number of time degrees of freedom, temporal degrees of freedom, the total degrees of freedom becomes 10 billion. And using the space-time reduced order model, we were able to reduce that number of degrees of freedom to only 10. And because of that, the original full order model, why is it not? Yeah, the full order model, which need to be simulated using the 256 cores for 17.4 seconds, we were able to finish the calculation using only one core within 0.006 seconds, which gives you a world time speedup of 2,700. And the accuracy was really good also, the less than 1% relative error. All right, and that was the topic I would like to introduce. In addition to the nonlinear manifold reduced model, the last topic I would like to introduce, I just want to briefly introduce that, is the component-wise reduced model. These days, the lattice type structure is very, of interest by the many researchers because of the additive manufacturing capability, like 3D printing, the techniques we have these days, which can manufacture the very complicated structure such as the lattice structure to achieve to maximize the strength with a light weight, for example, and it is actually manufacturable. But using the mathematical algorithm, we can actually find out the optimal lattice structure by going through some optimization process. And however, those optimization process is very computationally expensive because of this complicated geometry, and using the finite element, traditional finite element methods, it's basically not durable. You cannot run it even with the high performance computing we have at the Lawrence Livermore National Lab, or it'll take really long time. So we need a faster algorithm, and the component-wise reduced model gives you those formalism. And for example, using the component-wise reduced model, when it is applied to these simple problems, where the blue is the original the lattice structure is optimize the shape, and so that at the end the optimization algorithm will pick up this red area to keep, and the blue area to throw away, to maximize the strength and minimize the mass. And we were able to accelerate this procedure using the component-wise reduced model by a factor of 660 speedups. And what was the one advantage of this types of method? It's a tunable accuracy. If you want really precise solutions, you can simply add some the basis, and the accuracy becomes like less than 1% relative error to like machine precision accuracy. All right, that was the second, the last topic I wanted to cover. And now let me conclude the talk with some summary. I hope I have introduced many interesting use of the model techniques, data-driven and physics-constrained approaches. The examples I have shown you include the black box approach, the deep fluid on 2D Burgers equations, and the linear subspace reduced model applied to various Lagrangian hydrodynamics, including seed of blast problems, and the nonlinear manifold reduced model, the nonlinear manifold reduced model to handle the advection dominated problems efficiently, and also introduce the space-time reduced model briefly, which is applied to the large-scale transport problems. And also, I have introduced the component-wise reduced model, which it was very useful for lattice structure design. And also, I have introduced the Libram open source code, which you can take advantage of it. And if you are interested in knowing more about the projection-based reduced model. All right, I hope that you have you find the things that I have presented today useful for your applications. Please let me know if you are interested in it. We can build up some collaboration from now on. All right. With that, let me conclude the talk.
Okay. Let us thank the speaker for the really interesting talk. And now we have time for Q&A. So please use the raise your hand feature so I can call your name and you can answer your question. Or if you want, type the question in the chat or the Q&A feature. And I just saw we have two in the Q&A feature. So Nick, do you want to ask your question or should I read it? But let me give you a second. I can. You're allowed to talk. Okay. So Nick, please go ahead and ask.
So this is a question about computing gradients via finite differences. And then so the question is like maybe your reduced order model can accurately capture the function, but perhaps the gradient is not so accurately captured. And I was just curious about your experience computing gradients via finite differences with the reduced order models.
Yeah, you're right. I mean, the computing the finite difference and approximate the gradient with the finite difference is tricky business. There is the step size you have to the fine-tuned. If h is too small or the step size is too small or big, then your finite difference approximation will be very poor. So you have to to choose the right step size. And however, this local reduced model is very accurate where the point you are trying to predict is closer to your training points. And the finite difference at the end of the day, you want the step size to be small, right? Too small is bad, but reasonably small. And the reduced model, the solutions will be able to give you a pretty good the accuracy. And if the subspace you are using in the reduced model is containing the neighborhood of that training point well enough, then the gradient is approximation from the finite difference will be well approximated.
I was wondering if maybe not even doing finite differences, maybe sort of taking some sort of local average gradient over a small region, or sort of the convolution of the gradient with a Gaussian function or something of that nature to get sort of a local average gradient, which would be more robust to oscillations in the model.
Right. Well, yeah. I'm sorry. I was distracted by this message, but you're talking about for some of the functions, very oscillatory functions, the finite difference will not do a good job of the approximating the gradient. Is that?
Yeah. The concern is, what if the function isn't oscillatory, but the model is? The reduced order model is.
Oh, the reduced model. Okay, so it won't be that oscillatory I wouldn't worry about that aspect. I mean, the other, opposite case, I would worry about, like if the model is too oscillatory, then you really need to, use the very small steps to capture the, the good approximation of the gradients using the finite difference. But if the model is not that oscillatory, but it's not a problem because the reduced model, the linear subspace reduced model, it won't be oscillatory because at the end of the day, it is representing the solutions in the underlying the linear subspace spanned by some the reduced spaces. So
that's interesting. Okay,
yeah,
so
it won't be
somehow it also kind of regularizes the gradient in some sort of way.
Yeah, exactly. It smoothes things out, by introducing the reduced spaces, whether it is the nonlinear manifold or the linear subspace, even more so for the linear subspace. So
okay, great, thank you.
Yeah.
Okay, I think we accidentally closed your video, so you can open it. So we had some technical issues. And
okay.
Sorry for that. And yeah, we have a second question from Pan. So please, Pan, go ahead and ask your question.
Thank you. Yes. So thank you for the great talk. So could you comment a bit about the offline computing cost for constructing the space-time ROM?
Yeah, that is a wonderful questions. So my screen is stopped shared right now. Do you see the shared screen?
Yeah.
Yes, we can see it.
All right, great. Okay, so about the space-time ROM. Okay, so the one nice thing about this space-time ROM, it's the offline cost is at just the same level of the computational cost required for the spatial reduced model, because we are using the same singular value decompositions. And I'm not sure how much you're familiar with the singular value decomposition. If you do the singular value decomposition on some the simulation data matrix, you will get the left singular matrix and right singular matrix, and in the middle you will get the singular value, the matrix, right? Mm-hmm. And usually, to obtain the singular value, the spatial the reduced spaces, we take the left singular matrix and truncate that, and use that truncated version as a spatial the basis, reduced basis. But if you look at the right singular matrix, what the right singular matrix does is each row of the right singular matrix of the transpose is describing the temporal behavior of individual corresponding spatial basis vector. So using that fact and using that observations, what we do is we just do the one singular value decompositions and take the left singular matrix and form a spatial basis, and use the right singular matrix and form a right singular the temporal reduced basis, and combine those two using the canonical product and plug that into the. So the computational cost, bottom line is the computational cost of the space-time reduced model is as expensive as the spatial, the computational cost for the offline, computational offline cost for the spatial reduced model. So it's not that more expensive than the original spatial reduced model. Very good questions though.
Thank you.
Yep.
Okay, so I think we had the full hour. If we don't have any urgent questions, so please, if you have one, use the raise your hand feature. But if not, I would like to keep the colloquium on time. We have another talk next month, so please go to the website or wait for the email about the speaker we have next month, and looking forward to see you again. So let us thank the speaker again. It was a really nice talk and really interesting. And yeah, please contact him if you're interested to collaborate in future. Thank you so much for joining the Cairo colloquium. Bye-bye.
Thank you. Thank you, everyone.